All right, so we're going to look at this example of frictional forces on flat belts because it's a little bit different. So usually you'll be given the problem that'll say like, okay, so we've got some tension 1, some tension 2, and there's this belt on this, I guess cylinder or whatever. And it'll be like, okay, so those are separated by some kind of an angle beta, and the impending motion is this way. All right, and so kind of think about it like if I'm standing here pulling on this like little, I don't know, pulley belt thingy. If I'm trying to get it going this way and I'm like, all like angry trying to pull on it, then like a little like puppy, little tiny puppy, kitty, never mind. I can't draw puppies, so it's going to have to be a kitty. Kitty is over here and she's like casually holding onto it with her weird body. This is supposed to be a cat. So Kitty is just kind of casually holding on to it. How come Kitty can hold it? And that's because even though I'm trying to get it to move, Kitty, when she pulls on it, actually only has to pull a little bit because all these frictional forces from this contact are actually helping her to pull on this. So even though I'm going to win, because it's impending motion, she doesn't have to work like nearly as hard. I have to work super hard. So instead of naming these T2 and T1, because I always forget these and I get them confused, I'm going to name this T like, I don't know, like driven or like angry or like T super irritated. I don't like saying the word angry. We'll say this is me super irritated. And then Kitty over here is just lazy. So Kitty doesn't have to work that hard. I have to pull way, way, way harder. So I guess this will be TI and this will be TL. Okay. So that's kind of what we're going to look at in general and see how are those related. So the only way that this can work is that, again, T irritated has to be much greater than T lazy in order to overcome all the friction. And the question is, well, like how much does it need to be, I'll say to get impending motion, how much stronger do I need to be than Kitty in order to make this happen? Okay, so kind of what we'll do, come over here, is just look at like a portion of that circle. So I'm going to kind of draw this a little bit bigger. And we're just going to look at one arc of that circle where all those little blue arrows are that I drew. So basically what we're going to do is we're going to take this and we're going to like just cut this like a random slice like right here and look at that. Okay, so I'm just going to draw that out over here, wherever I started that. Okay, so something along these lines, and there's this tiny, tiny, tiny sliver d theta. Okay, and this is kind of stupid, and I get if you don't like it, but that's just the way it goes. I'm going to bisect this angle. That's a really, really wiggly line, but this is in my y direction. And so basically what I've got here, and I'm bisecting it because I want to make like my normal tangent to the surface. So there's a belt like right here, okay, and the belt is going this way. Okay, so if I'm looking at the normal force of the belt onto the sphere, or onto the cylinder, not the sphere, the cylinder, I would have this itty bitty normal force of that itty bitty part of that belt. And there would be an itty bitty frictional force. I can't draw straight to save my life right now. This itty bitty frictional force that is impending motion. So since it's impending motion, I know that it's mu s dn. I don't want to write my s every time, but I guess I will. Mu s, and it's not just, dn. I forgot to write my D. So US itty bitty DN. And then as the belt is obviously shaped like this on a grander scale, then there's going to be a tension over here. And again, I've just kind of exaggerated that angle. And this is going to be some tension this way. And then this is going to be some tension this way. This tension is going to be an itty bitty bit bigger than the other tension in order for this to work. Okay, and so kind of how we set this up, and it's a little hard to tell because this is a terrible picture. So if the way that we kind of design this is say, okay, so if each one of these bisected angles is d theta over 2, then we can say, okay, then these up here would also be d theta over 2. And I'm pretty sure if you don't like calling it d theta over 2, you can actually do the whole thing and just do them all as d thetas. And I think it all ends up coming out in the wash anyway. Maybe it doesn't. I don't know. This is the only way I've ever done it. But just the idea is we're really, really, really zooming in. So we're getting so close. Those angles are the same. And we're just going to do sum of forces in the x and sum of forces in the y. So let's start with sum of forces in the x. So I've got t cosine, come here, t cosine d theta over 2, right? That's this dude. And then minus t dt, or t plus dt, and then that's going to be cosine theta over 2, cosine d theta over 2, cosine d theta over 2. And then what else do we have? Anything else? Oh, yeah, and then the df. So that would be us dn, and again, in the positive direction. So plus mu s dn equals 0. Okay, so basically I took a portion of this one, and all of this dude. Okay, so let's kind of see what we can get if we make this pretty. So I can distribute stuff, and I've got cosine d theta. I'll just write it out rather than saying it. Cosine d theta over 2 minus, and I'm distribute that, t cosine d theta over 2, and then minus dt cosine d theta over 2. And we'll say that is equal to negative mu s dn. Okay, so clearly, these cancel out. These cancel out in red because it's better. And so I end up with dt cosine. That was not a very pretty dt cosine. So I end up with dt cosine d theta over 2 is equal to mu sub s dn. Okay, now at this point, you're like, I don't know what that does. So one of the things that we kind of do here that's, I guess, kind of neat, is think about what happens. So if I look at a graph of cosine looks like this, right? Well, except, normally this line goes like here, chirps, okay? And the height of cosine we know maxes out at 1. Okay, now if I zoom in on this, that's not obviously supposed to be right there. It's supposed to be like right there. And as I get itty bitty bitty, so not only itty bitty, I'm itty bitty divided by 2. As I zoom in on this circle right here and I kind of see what's going on, that really as I get closer and closer and closer, and I can't get any closer with my mechanism, I will get that basically that cosine is going to be 1. It's not exactly 0, but as the d theta over 2 approaches 0, then cosine of d theta over 2 approaches 1. Come back here. 1. Like that. Okay. So what that means is I can rewrite that cosine theta over 2 as 1. So that gives me dt is equal to mu s dn. All right. So I'm just going to hang out with that guy for a while. Okay. Now let's do the same thing, but we're going to do sum of forces in the y. So let's do that. I've got sum of the forces in the y. Who's all in the y? So I've got the dn is in the positive y direction. And then the 2 t's, but now I'm going to use the sign of the d theta over 2. So, and these are both pluses now. So plus, no, these are both minuses now. Oh man, adding is hard, especially when it's subtracting. Sine d theta over 2 minus t plus dt sine d theta over 2, like that, and that equals 0. Okay, so what does that give us? dn, and then that's going to give us 2 of those t sine d theta over 2's, and then dt sine d theta over 2. All right, and now before you get too excited, then a lot of people go, well, I know what the next thing is, because clearly if I look at sine, it looks like this. So clearly, if I get close enough, then as d theta over 2 approaches 0, then sine of d theta over 2 approaches 0. And I'm like, yeah, but that's only when it's exactly there. So if you kind of think about what was going on with cosine, kind of asymptotically, not asymptotically, but close-ish-ishness approach. So the cosine was like that, right? Except it was better drawn. Like it gets closer and closer and closer and closer. This doesn't really get closer and closer until it barely touches it and leaves. It's just like shroom straight through the center. And in fact, if the idea, dang it, the idea is if you get close enough to this that it kind of looks like a straight line, right? So if you kind of just zoom in here, that if I had drawn it perfectly, that this, as you get closer and closer and closer, sine of x in general is approximately equal to x as x goes to 0. Now, obviously, when it's 0, it is 0, but that also meets our little criteria here. So actually, what we're going to say here is that I'm just not having any fun with my eraser today. What we are going to say is that the sine of d theta over 2 approaches d theta over 2 as d theta over 2 approaches 0. And so this sine of x being x and the sine of x being, or the cosine of x being 1, this is stuff you're going to see a lot in these proofs that we do. Not just in this particular example, but in a lot of examples in statics and dynamics when we're kind of going closer and closer and closer, we're going to make those approximations. So now that I've got that, I've got dn minus 2t. Sine of d theta over 2 is about d theta over 2 minus dt times d theta over 2 is equal to 0. And then this is another one of those like hippy-dippy math things, and I can say that because I love math. It makes me so happy on the inside. These two I'm going to leave alone for just a second, well, except the fact that I'm going to mark that 2 off. But basically what we have right here is we have 1/2 of dt times d theta equals 0. And so basically what we do, and I'm sure like a fancy way to do this mathematically, but because we're engineers, we're like, whatever, it's close enough. You can basically say itty bitty thing times itty bitty thing is thing so small I don't care about it anymore. Like I'm officially done with this. You have failed to establish that you matter to me. And so basically we're going to say itty bitty times itty bitty, right? So, 10 to the negative 72 times 10 to the negative 72 is just going to be an overflow error anyway. Not an overflow error, it's just going to come to 0. I'm going to lose the precision. I'm trying to make a computer science joke at the top of my head and I wasn't ready. But basically that's going to go to 0. So I'll have that dn is equal to t d theta. Okay, so that was fun. So I'm going to take those two things, that thing and this other thing that I had over here, and I'm going to put them together. So I had dn is equal to t d theta, and I had mu dn is equal to dt. All right, so I can do this. So I'm just going to plug this in here for dn. So I've got mu, I got a stupid s, keep forgetting, mu s t d theta is equal to dt, and I'm like, all right. So I want to figure this out, so I need to isolate my t's. So mu s d theta is equal to 1 over t dt. So clearly I'm going to integrate both sides, derp to derps, and we'll say we're starting from 0 and we're going to beta, and then we're starting at, what was this dude? This was lazy. So we're starting, that's not how you spell lazy. We're going to start lazy and we're going to get to irritated. Okay, and this is just because I always forget which one is 1 and which one is 2. So that's why I'm saying lazy and irritated. And because I'm super, super good at math, I know that if I integrate d theta, because this is a constant, that I'm just going to get theta from b to 0. I'm kind of a genius when it comes to integrating constants. So I've got mu s beta here on the left. And if you really want to get obnoxious about it, it can be like, it's beta minus 0. And then on the right, I have the integral of 1 over t, which is the natural log of t, getting evaluated from irritated to lazy, okay? Because I'm even better at college algebra than I am at integrating constants, that's going to be the natural log of irritated minus the natural log of lazy. And again, I happen to know, again, being kind of an algebra genius, that this is going to be the natural log of irritated, I should have picked a shorter word, irritated divided by lazy. And for my final act of valor and bravery, that means that E to the mu S beta is equal to T irritated over T lazy. So that means that T irritated is equal to T lazy times, there's supposed to be 2 in there, E to the mu sub S B. And this is neat. Now, something that's really cool about this. So basically, if I want to be irritated, and if irritated wants to be lazy, so the biggest problem is flipping the direction. So if this is where impending motion is. Impending motion, that's the tension on this side. This is the loser side, the side that's not winning. But I want to call them the loser because they're like holding their own without actually trying that hard. If you get those in the opposite directions, then you're going to get the opposite answer that you want. Not the opposite answer, you're just going to get a bad answer. Another thing you want to think about is remember that this is unitless. And so in order for this to work, the beta also has to be unitless. Because like say you put the beta in degrees, then you'd have an answer to the degrees. It's not even degrees, it'd be to the degrees, which doesn't really make sense. So that means you have to use radians. I can't write this any bigger. I mean, I could. Have to use radians for beta, because if you don't, then you're going to have some kind of a unit up in an exponential, and you really want this to be unitless because this is newtons and this is newtons, or this is pounds and this is pounds. So you don't want to have any units coming from that exponential. Another thing that's kind of a weird little side note is it's independent of radius. So there is actually, it doesn't matter how wide the tree is. If you're trying to do this, it just happens to matter the coefficient of static friction and how much, what that angle is. So doing this around, if you're in a forest, doing this around a big giant tree or a teeny weeny tree, it's not going to matter as long as you're covering the same angle. And I guess on different size trees, it's easier to get a bigger angle. But if you were really careful about getting the same angle on all the same tree, then it would be the exact same answer. Woohoo!